My name is Pablo Doval, and I am working in a company called Plain Concepts. I'm the principal data architect up there, and I do data stuff, basically. In my experience, I have been always related to data projects, whether it was transactional databases, traditional transactional databases, afterwards, Hadoop, Spark, big data. And for the last couple of years, I was working mostly on models, on the machine learning and deep learning part of the story. And that's a bit what I want to talk about. And trust me, it has been 2 amazing years, but it required a lot of time to study, to go through all the huge amount of information that we currently have, which probably is too much at some stages. I was speaking with someone in the audience about that earlier on. But sometimes I do have free time. And when I have free time, like maybe some of you, I watch TV series, TV shows, and I really like finding these beautiful pieces of computer literacy that we have in this series. Let me show a couple of them to you. Probably you will not be able to hear this. No, but never mind about the conversation, because the important part, I have it flagged for you. So this is CSI, you probably know the series. This lady is saying exactly this thing. I'll create a UI interface using Visual Basic to see if I can track the IP address. Wow, I love this kind of stuff in series. Every time they speak about computer science, we end up having things like this. But my favorite computer literacy moment is this one. And we've seen this in quite a few shows. You know, there was a crime or something, an investigation, and just enhance that, and you start. It doesn't matter, the pixels, whatever, it just enhances the picture, okay, magically. We all seen this. I got to talk about artificial intelligence, about machine learning, about deep learning, but trust me, I will go back to this when we are finishing the session, and it will make sense. But for the time being, just bear with me with that. So, AI. What's AI? What's AI? What's ML? What's deep learning? We always get a little bit confused about that. I have a lot of conversations about this, and I like to tackle this from a history point of view, and I think it's also cool to know where we're coming from, and then we will talk a little bit about what we have in the future and what's lying ahead. So from a history point of view, take a look at this picture here. We have, well, in this case, we have 2 gentlemen very well dressed. I think we have lost the sense of style in our job, by the way. We were talking about Paul Stein and Nick Metropolis, 2 very well-known physicians. They were working in Los Alamos, and in this particular picture, you can see a chess game. This is important, this is relevant, because this is 1954 in Los Alamos. And it's the first time that a computer software beat a human player playing chess. So obviously there's 2 caveats to that. First of all, take a look at this chessboard. Obviously it's only 6 times 6 rows and columns, so it's a simplification. And secondly, the individual they decided to play the game against had never played chess until 2 days ago, 2 days previous to the test. So obviously it was a little bit biased, but it's the first time that a software won a match against a human player. So we can consider that to be artificial intelligence, right? So let's move to the next one. 2 years after this, the Perceptron was invented. And Perceptron was, as you probably most of you already know, it's a function approximator that's able to learn and train itself based on known samples. So basically, if I pass what I know is the ground truth as an output, I can adjust my weights, and passing the same input, I will always get the same output. So this was automated in the same time frame into a mechanical perceptron, and we're talking about 1956, 1957. This is a mechanical perceptron. We're talking about, in this particular case, this was the Perceptron Mark I. They had 400 optoelectrical sensors, so they will see a picture, and they will classify the picture in male or female. To train this model, they use a logistic regression model, so to say, and to train it, basically they were acting on the weights using servos, using motors on top of the potentiometers. It's amazing. I recommend you to go to YouTube, check for the videos of the Perceptron Mark I, quite a story to see here. So everything was fantastic. It was so good in the sense of evolving the technology that they had already, that the Dartmouth meeting happened. So basically, 10 software engineers, computer scientists back in the day. 10 computer scientists met in Dartmouth College for the summer of 1956, and a lot of things happened during these 2 months. They were together working in this, but the most important thing is that they decided to put the name to the field. And this is the first time that it was agreed that this was going to be artificial intelligence. A lot of great and amazing stuff was happening these days. And actually, you will see in this picture, we have Claude Shannon, it's the father of information theory. And here, you can see that we have this guy here in the middle smiling. He's having a really great time. That's Marvin Minsky, a brilliant mind, a brilliant person, but at the same time, the evil figure of our story. So we'll go to Minsky in a minute. Remember his face, by the way. So, great times, as I was saying. Less than 10 years afterwards, we had Ivanchenko developed the multi-layer perceptron, which was basically combining together perceptrons units. So it's basically the first neural networks, artificial neural networks. But obviously, when everything goes so well, we know what's going to happen, right? There's going to be some kind of problem or something is going to happen. And in the case of artificial intelligence, probably you all have heard of the winters of artificial intelligence. We have went through 3 winters in artificial intelligence, as they are called. I'm just going to talk about one of them very quickly, because it's relevant. Remember the smiling guy in the middle, Marvin Minsky. He's Marvin Minsky with Seymour Papert. Seymour Papert is, by the way, the father of Logo, the graphical programming language of the 80s. 70s and 80s, and they wrote together this book, which is called Perceptron. And I don't know you, but when I see a book that's called Perceptrons, I don't know you, but I would expect the book to say good things about the perceptrons, right? So, well, something on this book was not so good, and it's something as simple as the fact that the perceptron cannot learn an exclusive or an XOR function. This is not entirely true. The thing is that they couldn't learn automatically a non-linear, non-separable linear function. But suffice to say that the moment that this was published, all the research on neural networks, all the research, or if you were researching on neural networks and hope to publish, you were going to have a hard time. It basically halted the development of neural networks. So what we did back then, well, one of the things that people say is, well, we can revert to expert systems, which are basically sets of rules, and having an expert deciding these sets of rules and programming them kind of in a manually programmed decision tree. But I'm not going to talk too much about expert systems because we are where we are without them. Just try to imagine the amazing robots, for example, of Boston Dynamics. If we have to hard code all the rules of the system, that's simply not going to cut it. So, since this was not going to work, we went back to the history as well, to the traditional models. We went back to statistical inference. Here we have Charles Galton as well. By the way, you see a pattern. Everyone that was living more than 15 years away from us, I think they definitely had a much better sense of style. So Charles Galton, it's just an example, in this case from linear regression. But the thing is that using traditional statistical inference models and the computing power that we had, we could improve the systems by using larger data sets, training over larger data sets, etc. And this is quite visible, for example, in Bayesian models. Bayesian models were not useful until mid-80s, early 90s, and obviously from that moment on, because of the computing requirements to train them. All the original filters, spam filters in your inboxes, were Bayesian filters. But the good things happened early 90s. Geoff Hinton, this guy here, with, well, obviously with other colleagues, published backpropagation. And backpropagation basically was a mechanism to guarantee that you could train a very complex neural network in a reasonable amount of time, applying the chain rule and making sure that all the activation functions were differentiable. I'm not going to get too much into that, but basically found a way of overcoming both the problem of the non-linear separation, the XOR problem, so to say, because it was not using linear functions, but also to train them in a reasonable period of time. So, this guy basically brought us here, to the deep learning model in which we are. Anyone recognizes this? Anyone? If I ask some of you, if you can tell me what this is? Sorry? Sorry, say again, I cannot hear you well. It's a CNN, that's right. And the specific name? AlexNet. I heard someone said AlexNet. Right, that's right. This is AlexNet. I don't know who said it, but very good job. Okay, so we can use neural networks, deep neural networks, to do a lot of things, from image classification, image segmentation, to knowledge extraction from tests, even to time series analysis. Valentina probably is around the room. She can tell you much more than I do in time series analysis, but using LSTMs, you can do very advanced time series analysis, so it's fantastic. But for the remainder of the session, I'm going to stick to computer vision, to image models, because it's easier to share, and I have to basically limit myself to something. So let's see an example. This will be very simple to classify. We have a set of ships there. So things to note is that this model can classify the white sheep very well. The black sheep, even if the color changes, it classifies it very well as well. By the way, I always try to pass this through a model and hope that it says this is Pablo's hair. And no, never happened. But it looks like my hair. Even we have a sheep here sitting, and it's detected as well. This is a very simple exercise on classification, but we can go for more challenging exercises. And the best example I've ever found is the muffin or Chihuahua challenge. So this is brilliant. Try. This is a challenge for me as well, so try to imagine for the computer. And well, we have more. We have the dog or mob challenge as well, so it's fantastic. So how does this work? I'm going to start talking about this from a non-deep learning point of view. What I'm going to be doing here is show how we will do it without deep learning, but using traditional machine learning model. Let's assume that I want to create a function, and this function wants to classify a set of pixels between a circle and a cross for playing tic-tac-toe. One very simple way of doing that is using logistic regression. It's a linear model, so I'm going to, sorry for going to very quick on this. This is not really relevant. The relevant part is the conclusion, so bear with me with that. So we will put all the pixels of the image in a unidimensional vector, and what I'm going to do is to add a weight to each of these pixels for each of the categories. So I give a weight to each of the 81 pixels for the circle category, and another one for the cross category. These weights, I initialize them to random. Somewhere there will happen some magic that will adjust these random weights so it classifies accordingly. But the thing to keep in mind here is that this will create this for me, which is the multiplication of all the pixels by all the weights, and finally adding bias, basically to compensate if in my data set I have 90% of circles and only 10% of crosses, for example. And this here is a linear function. It's actually the definition of a line. Okay, so I can use it to control the parameters, so to choose which observations I want to make part of one class or another. So I can alter the weights, and this is going to change the slope of my line, or I can alter the bias, and this is going to change the point where my line crosses with the tangent. Okay, but in this line here, I'm only depicting 2 dimensions. Now try to imagine this linear model, this linear in first 3 dimensions, then 4, then 5, then 6, and lastly, this is going to require 81 dimensions, because that's the number of pixels I have. Okay, well actually no, it's 2 times 81 because I have 2 classes. So once I have these weights, I can just add the values. It's going to throw me garbage, but the real here is we are going to try to optimize so the maximum value corresponds to the category that I'm trying to predict. So let's consider that I have these values here. Obviously these values are very different in range, so I'm going to add a sigmoid function to crush them into an interval between 0 and 1. That's great. Normally we don't use this. We can use this for binary classification. Normally we go for something called the softmax, which if I have 10 categories or 100, it's going to ensure that the sum of all the categories sums 1, which is a probability distribution function. Don't worry about that, but the key point here is this one. I know that this is a cross, and I know it because I'm training on a dataset that I know. So I can use one thing which is called one hot encoded, which in this case is going to show a 1-bit on the specific kind of category I'm using. So if this means category X and this means category circle, this means that this is an X. And then I can compute the difference of the output of the softmax with the actual values. So if I subtract those values, I get the error. I get the distance from my prediction to the ground truth. Now, if I add that through all the observations I have in my data set, all my crosses, all my circles, I can start adding things to my function, to my error function. And I call this the loss function. And this is the function I want to minimize. In this case, I'm computing the mean of all the data points, of all the observations. And if you realize, I'm also squaring them. And that has two purposes. One of them, getting rid of negative values. The second one, to make sure that the points that are more distant apart have more weight. Okay? So this is just one example of a loss function. But this is the key thing that I want you to remember, and actually why I went through all this. I'm talking about a very simple example here. I need to minimize this function. So to minimize a function, we all know from calculus that the minimum of a function, at least the local minimum, is where the derivative is 0. So I can start finding that point. But here I only have a function on a line, on one dimension. Okay? If I have one additional dimension, I have something like this. This is very simple. If I need to compute the minimum of the loss function, it's just the ball is going to fall until the place where the derivative is 0. But real life is not as kind. We can have something like this, which is going to be full of local minimums, but I can get stuck in a local minimum, how to find the actual value. And actually, this is, again, a 3-dimensional function. But if I'm going to try to find the loss function, the optimization of the loss function for a 1024 times 1024 pixels times 3 for the red, green, and blue channels, we're talking about a huge dimensionality here. So that's a challenge, and that's where the challenge lies. So this was a very naive approach. I just wanted to introduce two things, the optimization process and the loss function, and this issue with the dimensionality. Let's get back to real life and deep learning. Things normally evolve based on challenges. That's how we are, that's how we work. So there is this challenge, it's actually quite old, ImageNet, started in 2010, which basically provides a set of data sets. This one is the classification data set, which has many thousands of images in 1,000 categories. So we have there some examples of images and some examples of categories. So let's look at the history on the classification rates of ImageNet. And what we have here is, first time 2010, NEC America, large corporation, the error rate was 28%. Next year, Xerox, another large corporation, and we only went down to 25%. But what happened in 2012? In 2012, we have this thing called AlexNet. It's not a large organization, it was a university team, and they managed single-handedly to almost drop by 10% error rate. This was amazing. And actually, the more amazing is the fact that all the years afterward they are all based in the same things that AlexNet did for the first time, and we will get into that in a minute. But something magical happened in terms of advances in neural networks, deep neural networks, advances in GPU, and using the GPU, the graphics device, to find these optimization models. And basically this is, this was the moment where everything started for the deep learning piece. So, again, we are here back. This is AlexNet, the thing we showed earlier on. This was, again, where everything started. So, how does this work? Very quickly, if I want to find that this cross is really a cross, what I'm going to be doing is the following. I'm going to base myself in filtering. So, I can see that there are three main features here. This diagonal, which is replicated here, this diagonal, which is replicated here, and the central cross. So, I'm going to create three filters, which are going to share these characteristics. And I'm going to then apply these filters to a part of the image. So imagine that I get this windows, 3 by 3 window, and I do a dot product. So 1 times 1 is 1, minus 1 times minus 1 is 1 again, minus 1, and I do that for the whole process. I have a perfect match here. So if I do this with this filter, the match is not perfect because obviously the filter is in the other direction. And if I do it with the other one, it's also not perfect. So I can then convert this filter matching to just one single scalar number. And this scalar number is 1, in this case, for example, 1 plus 1 plus 1, all 9 times, divided by 9. So what I can get with this is convoluted operation of the dot product of the filter through the image, which means passing this window through all the elements, and I get this here. And take a look at this. This is the diagonal. I'm checking the presence of this feature on the image, and the output is that it's 1%, so exact match here, here and here. I can see the diagonal here. That's where we can see that the filtering is working. So I can do the same thing with the rest of the filters, convolute them through all the image, and if I have these 3 layers, one on top of each other, I see the cross, okay? So, we have other pieces, like pooling, very, very quickly. Pooling, which also was used for the first time in AlexNet, is basically scanning a window, normally a smaller window, and using an aggregate function. In this case, I'm going to do a max pooling, which is going to take the maximum value of that window. I can do it with the strides, so stride 1 will move from here to just 1 pixel, and then another pixel, and stride 2 will move from here 2 pixels, 2 pixels. So I get a couple of benefits from this. First of all, well, anyone can answer what's the benefit of pooling? Any ideas?
You can shrink the dimension.
That's very good. I shrink the dimensions, so computationally that's better. That's going to enable me to have deeper and deeper networks. That's good, but there's another one, which is the fact that it allows to reduce overfit because it's generalizing. And that's the key to max pooling or to any pooling. Okay, so we also have activation functions. I'm not going to talk about them, but basically I don't pass directly the values from one layer to the other. I pass them through a non-linearity. So a function that allows me to model non-linear behaviors, and this is what allows me to overcome the famous XOR problem I was talking about. I'm missing something here. Anyone knows what I'm missing? I just invented the filters myself. If we go back in history, we think about some high top cars from the 90s. There were some cars in the 90s that already had cameras that will tell you if you pass through a signal on the road, it will tell you which signal is it. Right now we can think about how to do this with deep neural networks, and it's trivial. But how do they know, how did they implement this back in the day? Well, basically the same thing. They use deep neural networks, they use convolution, but they had to manually draw the filters. So they had to create a filter which was a circular thing with a number in the middle to try to identify the maximum speed, or a triangle thing in different aspects. It was very, very, very time-consuming to build the models. So one of the things that AlexNet wrote is the fact that these filters get created automatically for you. They learn. So if I train my model on medical imaging, on X-ray scans, on CTs, it's going to learn the specific filters for that. If I train it on cars, on faces, it's going to learn another set of filters, like you can see there. So we have other kind of structures. We have autoencoders, which is a mechanism that we use mostly for unsupervised learning. People say that we can use them for compression. Don't do it. They compress, but that's kind of the byproduct. And they are not good at compressing because they are very, very specific to the dataset you are training with. I'm not going to get too much into the autoencoder because I've seen the 10-minute warning sign. Recurrent neural networks and long short-term memory cells, fantastic mechanism to implement time series, fantastic mechanism to implement sequence modeling. So every time you're using your mobile phone and you're using a predictive text application, this is basically what's happening under the covers. I could share a couple of stories if you're interested afterwards in the in the sofa there. So now let me tell you about a couple of projects. First of all, one of the projects I'm most proud about, I'm quite old, by the way, I don't like to admit it, but I'm quite old. During these years, you know, we all have sins. And this is kind of the project that allows you to earn karma points, as I say. Okay, because this is any healthcare-related project for me is a karma points project. This was done for a hospital in Spain. They had 19 years worth of data from mammographs, scans, and basically we used two different kind of models, stacked autoencoders and deep convolutional neural networks, not just to identify where there might be a cancerous anomaly, but also to classify, using a standard classification, a standard medical classification, the specific type of anomaly. Also, in addition to this, we have done some work on counting crowds on retail areas, but also on public surfaces, public events, etc. We all know the footfall systems, on the ones of you that works in retail, they really don't work that well. There are these sensors at the entrance of the store. So counting by image is very hard, but very efficient once it's working. I'm not going to get into the practical details, but basically the key concept here that enable this to work well is dividing, splitting the input in a first global estimator, trying to understand if it's a large crowd or a small crowd, and then dividing adding more weights to the specific kind of estimator, the local context estimator. An additional one, applying style to images. We all have seen that you take a picture and you can apply a style of Van Gogh painting or whatever. That's not impressive anymore. It's basically, by the way, only using this, the way topology, the same topology that we are using to use an image classifier with multiple layers. We could get just AlexNet as it is, use the intermediate layers, change the loss function, and we will have a style transfer, an artistic style transfer application working. But this is very nice for images, but one thing that people don't normally think about is that we can use this also mixed with Kepstral analysis to mimic voices, to apply the style of a voice. So I can have Morgan Freeman. Well, not that I don't like my voice. Obviously, I don't have anything to compete with Morgan Freeman, but I can have an audiobook spoken by Morgan Freeman, read something to the mic, and it's going to sound like Morgan Freeman, more or less. So it's quite amazing. Now, I want to show you something. My favorite kind of models, generative adversarial networks. Have you seen these birds? None of them are real. They are not pictures. They are computer generated and not 3D. I just told the system, I want you to generate this specific kind of bird, and it does that. I have an application that, by the way, we developed as a test lab in AI labs for Microsoft, where you can just submit your sentence, and it's going to create, some of them are really scary, so sometimes I had nightmares with some of the things that I've seen here, but the thing is that they don't exist. They never existed. It's not images. It's not that I have a 3D drawing and I apply some textures that mimic what I'm asking. It's amazing. How does this work? Two neural networks competing against each other. So I have one generator that's fed noise and some features, like the length of the beak, the color of the feathers. And I have a discriminator, which is basically going to allow to evaluate from an actual image of a bird whether my noise looks more like a bird than this. So I have these two neural networks competing against each other. So at the beginning, the generator is only going to generate noise. It's going to be very bad. But with some thousands or hundreds of thousands of training processes, it's going to actually fool the discriminator. And each time it doesn't, the discriminator is going to be learning as well. So it's quite an amazing mechanism. It's a zero-sum game of neural networks. So this is being used for retail. For example, all these shoes have been dynamically generated by sentences that the user spoke or wrote. But now, do you remember that I started with this enhance that pixelian thing? Let's see this one. I'm going to go very quickly. You see this image here? This is the origin pixelated image. If I want to enlarge that, I have to use, normally I go to Photoshop and I use a big cubic filter and I enlarge that. This is the result, obviously it's not amazing. So what I can use is GANs and neural networks to have some super sampling like this. This is amazing. All these images, this is the input, this is the ground truth, the image as it was, and this is what generated from this input. This is amazing. I think this is one of the best examples you can see. So, okay, you all love this. Very quickly, what do you need to do to start doing this kind of projects? What do you need in your team, etc.? First of all, do you remember this? The cures of dimensionality. Training these models is really expensive. So you need GPUs, a lot of them, a lot of machines. You need a lot of memory. So you are not going to create a whole data center for this. It wouldn't make sense. Just use any kind of Azure resources, cloud resources. So you have Azure, you have AWS, you have a lot of mechanisms that allows you to train at the scale you need at the moment. Don't even try to have local environment, because I can tell you we don't. What else do you need? The framework to write this. So there's a lot of frameworks. We are starting to look like JavaScript developers with all these frameworks, Vue or whatever. This is crazy. But now it's not so important. Well, first of all, the good news is that stick to TensorFlow. That's going to solve most of the problems. Secondly, if you don't stick to TensorFlow because you need to execute the inference in a device that is not able to execute it, and you cannot load a TensorFlow model, Onyx comes to the rescue. This is a project that has been running for more than a year, and basically it's a binary serialization mechanism that allows you to have this TensorFlow or Caffe or CNTK or whatever model running independently on each of the different runtimes. What else do you need? A team. Now, I know I'm a little bit late on time, just one additional minute for the team because I think it's important. My advice, I have a wonderful team. I lead a great team with great individuals, and almost even better, great projects that we have been looking to be engaged into. And one thing I can tell you, sorry for all the PhDs here in data science. So you are extremely valuable, guys. But one thing that I want you to understand, you need to cover the data engineering part as well. You cannot just have 5 data scientists, PhDs, brilliant team of members running on a office space for 1 month and expect to have something that it's deployable in production and it's not going to have issues. So you need the skills from all parts of the world. This is really, really, really important. Probably this is the most important thing I'm telling you all today. And lastly, and with this I'm almost done, you need a plan. Even if it's a very simple plan, but how to deploy things. How you're going to be deploying your things. You don't want to have a Python script running there. So we now normally use Kubernetes and a mechanism that allows you to scale and deploy to different pods, etc. I'm not going to get into the pipelines, but my advice, if you have not read about any pipeline, go find a paper which is called TensorFlow Extended, TFX, which basically is the Bible, the holy grail of the model serving papers, which explains what you need. The tool you use, there's fantastic tools around, doesn't matter, but you need to understand what you need. Canary mechanism for A/B testing, deployment of the models, pipelines for test and training for training and inference to be consistent, really important. So, last piece of advice, this is moving really, really, really fast. So one of the things I mentioned from time to time is that last year, this activation function, which is called swish, which is x times sigmoid of x, was released in a paper, and in 4 days it was put in production. So it's extremely quick the way this is amazing. This same thing happens with the capsule nets, which is kind of the new convolutional neural networks, so to say, by Geoff Hinton. So keep on reading. Read the archive, there's a lot of materials around, and especially engage in the communities, which is the best part that we have. With this, I'm done. Thanks a lot. I know I overused some minutes of your time. Thank you for that, and if you have some questions, I will be there. Happy to answer. Thank you.